Hello, hello, hello. Welcome back. It is Wednesday, the 18th of March, and today we are going into some thermal physics. I know I put the poll to the Discord server, and a bunch of you would have suggested, "Ooh, nope, Adblock did a thing. Stop teching." Right, so a bunch of you voted. I say a bunch of you. There were like 5 votes. It was great. But thermal physics came out on top, and so that's what we're doing today. Hello, hello, hello. So feel free to join the Discord server and suggest other topics for future streams, and that'll kind of dictate how we do this. Because if you're the ones who are here, it makes sense that you guys get to be the one to determine what we do on any given day. So today is Thermal Physics Day. I have got the AQA book because that's the one I teach the most. Hello, Edwards Integrals. And I've also got some supporting online notes if we need to. If you guys have any particular questions from past exams that you think are like good for a specific topic like this, feel free to drop them in chat and I can kind of like ditch what I'm doing and kind of go out and do that. Because I know a lot of what I'm doing here with the physics stuff, at least, is very like seminar based. It's lots of me monologuing, not as much of me doing practice questions in the way that I do with the math. So if you guys have any suggestions or things you want me to do, yeah, OCRA. Yeah, this is AQA. So I can find some specific questions from OCRA if you want. Just in case, although I do think OCR isn't as supported online as the AQA. Let me just check that real quick while I'm here. Classic sort of side of the streamer's face as they look at the second monitor. Where's thermal? Where's thermal in here? May be helpful just in case. Let me have a quick look. Thermal. All right, I'll have that open on the side in case I want to get into it. Yeah, it's just not as supported on this platform. Okay, but at the very least, we'll go through the core theory. This will be thermal physics. This may then dip into gases as well, because I think those two go really hand in hand, where a lot of the thermal physics stuff is going through like internal energy, specific heat capacity, specific latent heat, that kind of stuff, the macro level stuff. I think it also makes sense to go on a like micro level and talk about gases. So I may combine the two, and if I do, then I'll make sure to change the title. And as always, I have a 6:30, so I got to keep it to a tight 1 hour, which I think also makes good use of your time. Keeps me honest. It sort of keeps me on track. And as always, if you guys want to ask specific questions, I'm always going to be here in the chat, so I can kind of deviate as and when. So without further ado, let's begin. So it's going to be a Miro whiteboard today. Okay, so I'm going to be supported from the textbook, as I said. Let's kind of just track through just to make sure I cover all the bases I need to cover. Thermal physics, right. The first thing we know about thermal physics is the concept of internal energy. So internal energy is the sum of all of the kinetic energies and the potential energies of the particles. And that will become important when we talk about ideal gases. But for now, let's just talk about that. The reason why that matters is when you heat a material, because we're talking about the internal energy will always rise. And because the internal energy is made up of the kinetic energies and the potential energies, whenever I'm putting energy in, one of those two is raising. Do we have to say the random distribution of them? I think that's going to be, again, more when you talk about gases, the fact that they have random speeds in random directions, as sort of laid out by the Boltzmann distribution. That feels more gas to me than straight sort of thermal physics, but that is relevant. Now, when we're talking about it raising the internal energy, like we said, that is either going into raising the potential energy side of things or the kinetic energy side of things. And that depends on what that heating is doing at any given time. If you are raising the temperature, then that is raising the kinetic energies of the particles, because temperature itself is a measure of the average kinetic energy of the particles. Really important core definition that. So if you're raising the temperature, you're raising the kinetic energy while the potential energy stays the same at the same state. Or you are changing state at a constant temperature, in which case the kinetic energy is staying the same and the potential energy is changing. So if you're kind of going up from solids to liquids or liquids to gases, then the potential energy is increasing. If you are freezing or if you are condensing, going from gas to liquid, liquid to solid, then your potential energy is decreasing. And so that's kind of everything from like a macro level, like a sort of high level, right? This is much more of a. I'll get to the depth, the graphs and the equations, but I think I want to start with the kind of more conversational based stuff. No one wants to see me writing things. I don't think just sitting here waiting for me to like write on the board is just like not it. But that's the basic idea. Now the first law of thermodynamics. Let me get the exact wording for you guys. So we have. Okay, so when energy is transferred to a substance by heating it, or when work is done on a substance, that is what raises the internal energy. So the internal energy is increased by either doing work or raising or by heating it. Is this mentioned in the AQA spec? Yes, it is mentioned in the AQA spec. Is it not mentioned in the OCR spec? Maybe not. It's not too much. So let me get into it. It may be that this is difference in specification. If this is not in your spec, obviously feel free to ignore. But the first law of thermodynamics from a sort of equation perspective, Gibbs free energy is not included in this. That is much more of a chemistry thing than a physics thing. So this is depending on your like the equation you've seen. You've either seen this with a plus or a minus. That depends on your definition of whether this is work done on the system or work done by the system. But the principle is still the same, that this is the energy supplied. And it's either going into internal energy or work done. For the purposes of A-level, I'm not going to stress too much about that sign and the differences between that and the engineering, but I think at a high level, just showing you this relationship between the energy you put in by heating and it's going like, and then there's sort of trade-off between internal energy and work done as a result of that. So we know the sort of structures of solids, liquids, and gases, I'm going to assume is kind of given for you guys. So I'm not going to go too deeply into that. Work done on the system is positive. That kind of depends. Work done on the system, I think, would be positive. Work done by the system would be negative, which is why I think the engineers use the negative of that. I can't quite remember the specifics off the top of my head. Well, let's think about it. So let's come up with an example, right, to help us make sense of this. If I am heating a gas inside an engine, say, and at constant temperature, that then causes a piston to move out, that system is doing work. And so the energy I put in, okay, so in which case, so in that case, delta U would be 0 if it's a constant temperature. The energy I put in would go entirely into work done by the system in order to move the thing. If we're talking about work done on the system, so for instance, if we are heating it and we are manually compressing it, those will both go into raising the temperature. So if we're talking about work done on the system, then that would become negative. So work done on the system, I think, should be negative. Work done by the system, I think, should be positive. And you can work that out from first principles by just sort of thinking about an example. Is the 0th law of thermodynamics? I know you love that 0th law. No, it's not. No, it is not on the AQA spec. Although, drop a comment, because I've seen you talk about the 0th law before. I don't know exactly what it is. So if you could enlighten me, that would be great. I've actually not come across that, at least not like by name. Right, so that's the idea of the first law of thermodynamics. Usually not the most important part of the spec when it comes to A-level. What does obviously matter is Celsius versus Kelvin, which I think you guys know about. I think it's important to know why we kind of came up with this idea of absolute zero, because we saw essentially just thermal equilibrium. Cool. So the 0th law is apparently if two systems are each in thermal equilibrium with a third system, then they are also in thermal equilibrium with each other. I guess that makes sense. But no, I don't think that's part of the A-level syllabus. So what we observed is, if this is temperature in degrees C, and this is pressure in pascals, what we observe is there is a straight line. Oh, that law is in the syllabus for you. Good to know. So what we observe is, as you go up to sort of 0 degrees C, we see that there's this pressure law. P is sort of proportional to T. As you decrease the temperature, you decrease the pressure. And it tracks then that if you were to follow that back, there would be a temperature at which the pressure is 0. And that would be your absolute 0. That's your argument for why we know an absolute 0 exists, even though we've never achieved it in practice. And by experimental data, you can track the line back and work out the x-intercept and find that you're talking about minus 273 degrees C for absolute 0. Which again is why I think temperature and thermal laws should always be taken in combination with gas laws. So like I say, I kind of want to move through it to make sure we have enough time to go through both. So temperature, this stuff is fairly easy. Let's talk about specific heat capacity, which again is fairly standard. Although the most important thing is going to be the experiment. They love to talk about that experiment. And sort of, yeah. So we know, again, this is sort of a classic. You guys know this from GCSE. Q equals mc delta T. Where m is the mass in kilograms, c is the specific heat capacity, which they love the definition of. Remember, it's the energy required to raise 1 kilogram of a substance by 1 degree C. And then you get the change in temperature in Kelvin or degree C. It doesn't matter because it's a change and the scale is the same in both. And Q is the energy supplied in joules. Now, practically speaking, most often you are supplying that energy using electricity, where you are supplying it with a constant power supply. So more often than not, you need to understand that that energy is a power times time for a constant electrical power supply. We have a question. Do you have to refer to it as Q, or could you use other notation, or would you be marked down for that? It's Q. Call it Q. Why? What else would you be calling it? Would you be calling it delta E? I would be trying to use Q whenever you're talking about sort of calorimetry or thermal physics. Cool. Yeah, I would avoid calling it E. It's very much Q. I don't know why, in fairness, but like it is. Because now we're getting to the point where you're right. Energy is either E for energy, W for work done, or Q for K. But yeah, is what it is. Delta theta I've seen in some books. Okay, for yes, delta theta sometimes exists instead of delta T, where the theta stands for thermal temperature things. Q is very much for the energy, and it's either delta T or it's delta theta. Oh, you've read in some books as delta E. Interesting. Those books might be American. It is what it is. I would say this is why these tiny discrepancies are why it's important to do lots of past papers, do lots of mark scheme analysis, so you know exactly the language that the exam board wants to see from you. Now, experimentally, how is this done? Yeah. So let's say so what we've got is experimentally, you would have some sort of electric power supply heating up a block of material, let's call it copper. So maybe you've got big block of copper, and we've got some sort of like heating circuit. Guys, I am so good at drawing, like you have no idea. And then you'll have your like thermometer, totally life accurate thermometer. Hang it in the Louvre. So you've got your heating circuit. Can I spell today? No. All right, so we've got our heating circuit, and we've got our thermometer, and we've got like our copper block or whatever. So the idea is we are heating it with a constant power, and then recording the temperature using a thermometer or like a proper temperature sensor. Temperature, what's the word for that? I feel like there's a word for that. Like, you know, the little electronic, am I saying thermometer gauge? Like, yeah. Chat, you can sort me out if I'm missing something. But so the point is we have to either or like an analog thermometer or like a temperature gauge. So one that does it a bit more accurately and precisely. But the point is you measure the temperature at different times. So time in seconds, temperature in degrees C, and then you can calculate delta T from that in degrees C or Kelvin. And by collecting that, you plot the temperature against time. And the gradient, well, let's talk about this. So the temperature will clearly be going up as time increases. And from rearranging this equation, we can say that delta T is equal to P over MC times T. So actually, if I have plotted instead delta T, it should be directly proportional. It should be a straight line through the origin, where the gradient would be given by the power over MC. So by measuring the mass of the block in kilograms using an accurate scale, and by knowing the constant power supply, by measuring the gradient, you can work out the specific heat capacity for your given solid. Really good experiment, that. Now, it looks like AQA does have the inversion tube experiment, which I went through in one of my Oxbridge interview series. But the way that goes is you have some lead shot in a column. So let's say you got your lead shot little things down there. The idea is that you invert the tube several times. So if the tube is length L, then when you invert the tube, the lead shot will fall to the bottom, and the change in energy would be M for the mass of the lead shot times G times L. And if you inverted it N times, then this would be the amount of GPE that gets converted into internal energy. And this thing would be equal to M times C times delta T, where the masses would cancel, and C would be equal to GLN all over delta T for measuring the increase in temperature of that lead shot. So those are sort of two ways. Now, this was the old method before electricity was invented, or rather before, circuits were like a thing. So that is one way of doing it. It's less accurate. Now, is another reason why they like this in your practical papers as well is because it gets you to talk about sources of error. In all of these cases, this assumes that all of the energy is going into raising the internal energy of the lead shot or the copper, as in the previous example. Not always so, because a lot of the times energy is lost to the surroundings. So you get heat loss to the surroundings, and you can begin to think about what consequence that would have on your results. So if we are assuming that all of the energy has gone into raising the temperature, but in practice it hasn't, in practice, we have achieved that raise in temperature with a smaller energy or a smaller input power. So the true power is the, hold on, you see, I always trip myself up on that. It's really hard to walk away, thread the needle on this. So it's easy to say, oh, heat loss to the surroundings. It's really difficult to sort of argue with yourself, all right, which way is that going to change your measurement of the specific heat capacity? But, okay, let me do this. Let me lock in. So, You are assuming you are measuring this delta T. If you are, so the delta T you measure is less than the theoretical, what the theoretical should be. So the theoretical delta T's should be bigger than what you get, which means the gradient should be bigger than what you get, which means the specific heat capacity is smaller than what you should get. Wait. I know this is so trivial, but I don't know why my brain hates it. It's always hated this so much. But it goes to show it's like, this is why you need to prep it, right? Because it can be conceptually hard to get round. So what would the true values be? These would be the actual. So the bigger that the specific heat capacity is, the smaller the gradient. So this would be theoretical. And we know from here that C is equal to P over M times gradient. So if the theoretical is gradient, then theoretically it should be smaller than what you measure. So you predict the specific heat capacity is higher. Is that true? Yeah, something like that. Or, well, let's talk about this in terms of, I think another way we can think about this is by, and if this is wrong, I'll definitely correct it. But another way we can think about this is the practical understanding of what the specific heat capacity is. So specific heat capacity is, like we said, it's the energy required to raise 1 kilogram of a substance by 1 degree C. So if you have a larger specific heat capacity, you require more energy to get the same temperature increase. Or for the same, yeah, so for the same temperature increase, you would require more energy. Or for, yeah, there you go. Or for the same energy input, you would get a smaller temperature increase. So in other words, by putting the same energy in, what would result in a smaller temperature increase? One of them is losing heat to the surroundings, and another one is having a larger specific heat capacity. So if you are assuming that all of the energy goes into the material, then the only reason for the dip would be the specific heat capacity is bigger. So this results in bigger measurements of specific heat capacity than the true values actually are. And that can be really difficult. And I encourage you to practice that for your practical papers, not just sort of saying, oh, this would be the source of the error, but beginning to think about what direction that would affect your measurements. Would it cause an overestimate or an underestimate of the true value? So in this case, our practical experiment would give us a higher specific heat capacity because we're suggesting we require higher energies to achieve the same temperature increase. When in practice, the energy that has gone into the material to achieve that increase is less than we think it is. So yeah, it's just tricky, and I really encourage you guys to get on that. Now, another way to use the specific heat capacity is to think about energy transfers, where in any thermal energy question, you need to be really, really careful about the story of the problem. So this thing is increasing or decreasing temperature. So for instance, if we have, hypothetically, block of material where this is at 100 degrees C, and this is at 20 degrees C, and this has a specific heat capacity of 320, and this has a specific heat capacity of 500. Making up numbers just for the fun of it. What would happen if we brought these two things in contact? Well, you need to tell, first thing you need to do is understand the story of the problem. So what's going to happen is the thing on the left is going to be losing thermal energy to the thing on the right. So the energy, we are going to assume that the energy lost by the thing on the left, so I'll call that A and I'll call that B. So I would always write myself out a word equation first. Someone says, is calculating C and calculating C at constant pressure different? You're only talking about pressure when you're talking about gases, and I'm not talking about gases right now, so I suppose these would be different things. So for this, I would always start by writing out the word equation. So energy lost by A equals the energy gained by B. And this sort of word equation will always guide my thought process if I then have to get really into the weeds on like how to set up this equation. So here the energy lost by A would be Q equals, and let's assume these are the same mass, M times C times the delta T. This will end up on a smaller temperature. So I'll say 100 minus the final temperature will equal the energy gained by B, which will be M times C times the delta T, which will be T minus 200, T minus 20, because that final equilibrium temperature will clearly be in between the 20 and the 100. And so we can cancel the M's and we can rearrange this. I don't know why I picked such numbers, but hey-oh. So 32012 minus 320T equals 500T minus 10,000. I think, yeah, let me just, because my brain's not braining today, so I'm just going to rely on the little trusty calculator. So 500 times 20 is very much 10,000, because I also just don't want to make a mistake. That would be rude to you guys. So it's for your benefit. You're welcome. So 42,000 would be equal to 820T. So 42,000 divided by 820 would give me a T of 51.2 degrees C. Now, why does this make sense, by the way? You can also think about that. Well, if we kind of think about this, you would think, well, the average, if these had the same specific heat capacity, would be 60. But we get something less than that. We get 51. Why is that? Well, this thing has a higher specific heat capacity. So you can kind of think of specific heat capacity as almost like thermal inertia, where this thing, the B, is harder to move its temperature than A. So it, like, B has almost more thermal inertia, so it doesn't move as far. It gets more weighted towards the B than it does the A. So that's one way to think about it. So that's one, for instance, that's why you can also think about specific heat capacity in terms of thermal conduction, right? So that's why, is that really? So if you had like, so metals, for instance, have very low specific heat capacities. It takes very little energy to get them up to temperature. Whereas insulators, you would want them to have a high specific heat capacity because you would want to be able to like bombard them with thermal energy, but still have them not move too much. So yeah, you can kind of think about specific heat capacity as almost like a thermal inertia, which may help you get to some sort of, which also might help you understand again what happened up here. If you're assuming all this energy's gone in, but the temperature hasn't gone up that much, you assume it has more like thermal inertia. So it's almost like the specific heat capacity is bigger than it truly is. Ooh, what if there are 3 metals joined at a junction and we have to calculate the temperature at the node? Well, that would be from that zero law of thermodynamics, which would be that this would happen when all 3 are at thermal equilibrium with each other. I've not seen this for AQA, but I will go through it just because you've asked and it's relevant. So let's say we had 3 things. So let's say, so like if that was 100 degrees C and this was 50 degrees C and this was 20 degrees C, for instance, then there would, what would happen is these would all become the same temperature, certainly. And it kind of depends on their specific heat capacities. So it depends if the final temperature that they reach is bigger than 50 degrees, because we know it's less than 100 and we know it's bigger than 20. But if it's less, if it's more than 50, it means that energy has flowed like this. But has energy flowed like that? I don't think I've covered problems like this, you know? It'd be really interesting if you can find me specific A-level questions that deal with that, because I can. That's clearly something I'll need to add to my repertoire in terms of teaching. I've not taught that. Huh. Happy to have a go in the comments. Sort of, yeah, see what you think about this. Oh no, you're not at A levels. Okay, well that'll be why. You only thought about two? Yeah, I think we're gonna leave this. Well done, you've bested me, at least for this live solve. Although that would be a very interesting question for Oxford Gentry. So maybe I'll think about adding that to the sort of repertoire. What I'll do instead is move on to change of state. So this is where we get latent heat involved. We know that latent heat is the... Ooh, can we look at it as three equations? The problem with that, though, the problem with thinking about the three equations is if the final temperature reached is bigger than 50, does it make sense to think of energy flowing out of the 50 into the 20? That's the part that I'm not quite sure about, and I would need to sort of do some further reading before I'm confident enough to state it declaratively as like in a sort of teaching capacity. Latent heat, we know, is the energy required to change the state of 1 kilogram of a substance at constant temperature. And so the classic graph that you guys are used to is the temperature time graph. So the temperature time graph might look something like this. I have started this ambitiously. So here we are heating the solid. Here we are melting the solid. Here we are heating the liquid. Here we are boiling. And here we are heating the gas. Now, as we saw before, the gradients of these bits relate to the specific heat capacities of the solid, liquid, and gas. And we can understand the specific latent heat from the sort of length of these horizontal bits. Because you measure the time taken for melting. So if I call this T melt, for instance, then we know that the energy supplied, yes, internal energy at each interval. You can, so in the first one, the internal is being raised. So this is part A, the kinetic energy is increasing. For this bit, the potential energy is increasing. Nope. The potential energy is increasing. For any heating, it's the kinetic energy that's increasing. And for any change of state, it's the potential energy that's increasing in this heating curve. And here, the kinetic energy is increasing again. So these are the changes in the internal energy as we are moving through the system. Kinetic, then potential, then kinetic, then potential, then kinetic. Because again, exactly. So one is not when one is increasing, the other is constant. So potential energy has to do with what state of matter you're in. So if you are constantly in a solid state of matter, your potential energy is constant. And here it's happening at constant temperature, where temperature is a measure of the average kinetic energy of the particles. In other words, the total kinetic energy of the particles is the same. And it's the potential energy that's changing as you're breaking the intermolecular forces or forming new intermolecular forces between the particles. So yeah, one changes, the other stays the same, but internal energy is always increasing. So it makes sense. At a solid, you have the lowest internal energy. At a gas, it's the highest. Exactly right. So here, if you take the time to melt, then we know that the energy supplied is power times the time taken to melt. And this thing would be equal to m L, where this would be the specific latent heat of fusion, which is the solid-liquid boundary. Specific latent heat of vaporization is what it would be called at this boiling boundary between liquid and gas. Huh. Okay. Now, this I think is fairly standard. Is there a question that I think would be good? I think the best questions here really involve understanding the story of the question. Oop, forgot to be at 100%. So here, well, that explains why it looks so thin. So for instance, let's say my classic that I love is, if you work backwards, how does it work? Okay, so if you're talking about a cooling curve, for instance, this would be the temperature, this would be the time. It's really just the same in reverse. Where the kinetic energy would be decreasing as you are cooling the gas. The potential energy would be decreasing as you condense it. The kinetic energy would be decreasing as we cool the liquid. The potential energy would be decreasing as we freeze it. And then the kinetic energy would be decreasing as you cool the solid. But it's otherwise exactly the same, where you need to consider, it would, yes, it is still called vaporization. Vaporization is just what it's called for the boundary. Because it also doesn't make sense then that as you're heating it, why would this be called the latent heat of fusion when it's the exact opposite of fusion that's happening? So they're kind of names for what happens when you come out of the liquid state. It sort of fuses going from liquid into solid, and it vaporizes going from liquid into gas, and they just have fixed names that are fixed for their boundary, as opposed to the function that it's called. Exactly, it's still called vaporization, even if you're condensing. Because it's the same energy, just in reverse, right? So when you're talking, it's not that the actual number would be different. It is the same physical quantity, so they just call it the same thing. I think a good thing here, again, really understanding the story of the question. So here, let's consider a classic, which would be ice cube going into water. I cannot remember the specific. And let's say the ice is at 0 degrees when it is put inside the liquid. So we don't need to consider the heating of the ice. But let's say, what is the specific latent heat of water? Oh, no, it's the specific latent heat of fusion. Yeah, cool. So let's say the water is at 25 degrees C, and there is 200 grams of water, and let's say we add 10 grams of ice to that at 0 degrees C. What you would need to do is first, always with any thermal question, write out the word problem first so that you know what you're doing at a high level. So what's happening to the ice? So the energy gained by ice, or the energy lost by the water, equals the energy gained by ice. So the energy lost by the water is I'm not falling for it. I nearly fell for my own trick. Look at the units, grams when it should be kilograms. M times C for water is 420. By 420, I mean 4,200. Q equals MC, and delta T would be 25 minus T because it ends up at a lower temperature. In fact, let me move this all over because that's too much of a gap. I want you to still keep the diagram. So this equals the energy gained by the ice. Now, what is the energy gained by the ice? It's ML 0. Well, actually, at this point, I really can't be bothered because, again, my brain's not braining. So what I'll just do is say it's 10 times 10 to the minus 3. So M times L, and L is 3.36 times 10 to the 5. Now, this is the energy to melt the ice. But once the ice is melted, it is water at 0 degrees C, not water at that thermal equilibrium temperature. So you also need to include the fact that that mass of water now, with a specific heat capacity of 4200, will raise to a temperature T from 0. And so making sure to include both those energies gained by the ice. So we're kind of going, if we consider this heating curve, we are here. We start here. We have to melt it and then heat it up. And we need to consider both of those energies separately. Cool. My value that I'm using for fusion is slightly different than the one that you quoted in chat. That's fine. You just take the one quoted. You never need to memorize these values. You just take them as given. So here, let me crunch the numbers. 0.2 times 4200 equals 840. So I'll simplify the numbers first just to make sure I don't do anything silly, because I'm prone to silliness today. I could just tell. I'm feeling much more relaxed, which means my brain is just like not it. So then we get, this is 3,360 joules plus 10 times 10 to the minus 3 times 4200 plus 42T. So 840 times 20, so 21,000 minus 840T equals 3,360 plus 42T. So 21,000 minus the 3,360. So 17,640 is equal to 840 plus 42, 882T. Please give me a good number. Do not make me look silly in front of the internet. Good. T is equal to a nice round 20 degrees C. So that ice didn't do much. So we would need to add more ice. That's not a lot of ice. But that is, in theory, how you would calculate things like this, paying very close attention to the story of the problem and then filling in the equations and rearranging as required. So that's certainly my top tip when it comes to any thermal question. Now, as always, feel free to drop in the chat if you have any interesting takes on that, if you've seen any particular questions on that. I need to now have a little ponder. Am I going to have time to sufficiently cover gas laws? Let me have a quick little think. Or should I do gas laws separately? I am certainly never going to do the full... Okay, I think we need a full session just on gas laws, mainly because of the kinetic theory. Yeah, some questions and then do gas laws next time. I quite agree, because gas laws, especially because like in AQA, they expect you to know the derivation of the kinetic theory, which is just bananas. And I absolutely hate it. And it actually came up on a paper once, which like screwed over one of my students royally. But you're right. Let's do gas laws separately. Let's spend some time thinking about fun, inventive questions that we can do for the thermal physics. These I've given representative examples, but let me see if I can go here and find anything of any interest. So, okay, this is interesting. So this is saying a metal ball of mass m is released from rest and falls through a distance h, reaching speed v at the bottom. The specific heat capacity of the metal is C. And then you got to find the increase in temperature of the ball. Well, this would be interesting. So again, with any sort of energy problem, I'm going to say, first write out the word equation so you understand what's happening. So what's happening is the GPE is going to kinetic energy plus the increase in the internal energy. So in other words, mg delta h would be equal to the kinetic energy gained, which is a half mv squared, plus the mc delta t. And this question is asking us to find an expression for delta t. Now, this delta T would obviously be due to air resistance in this model. We can divide through by m entirely, multiply both, multiply both sides by 2, would be equal to v squared plus 2c delta T. And then rearranging, we get 2, nope. I promise I'm literate, guys. I promise. Minus v squared all over 2c is equal to the delta T. And that is the expression as required. Ooh, come on, question. Okay, so this says next. Oh, hold on a minute. We got some questions. Maxwell distribution and some other gas laws feel pretty weird. No, because this is what I mean. So you have to think about the energy story. So what's happening is at the start you have GPE but no kinetic energy. As it falls, that GPE is turning into kinetic energy, but not all of the energy is going into kinetic energy. Some of it is going into raising the internal energy of the ball. So that is why I start by thinking about the story. Energy is going from where to where. So in this case, the energy is going from GPE to both kinetic and internal. So it's not the case that internal is kinetic plus GPE, because the kinetic energy is going up while the GPE goes down. So that's another way you can think exactly. So that's one thing. If you ever get stuck, think about which energies are going up and which energies are going down. So here, GPE is going down, kinetic energy is going up, internal energy is going up. So all the ups are on one side, all the downs are on the other. Okay. So then the premise of this question is that you have a meteorite falling to Earth. So we know that it is going to reach terminal velocity. And at that point, the GPE is still decreasing, but the kinetic energy stays the same. And all of the energy is going into either the internal energy of the meteorite or the internal energy of the gas as it sort of heats up the air it moves through. So we are going to say that it falls into a circular paddling pool at a temperature of 15 degrees C. Let me change up these numbers. Damn. Okay, so from this perspective, from this point of view, you would just be plugging in numbers, right? So if you say the height of the atmosphere, I don't think the height of the atmosphere is 200 kilo. Like what? Okay, so what we're going to do is we're going to give specific example. Let's say we're doing it from the height of the atmosphere, which is 100 kilometers. Let's say it reaches a speed of 100 meters per second. Let's say the specific heat capacity. Have they given us that? Yeah. So we're going to say this is iron with a set specific heat capacity of about 450 joules per kilogram per Kelvin. According to this model, we could plug that in to work out the delta T. So we would say that delta T would be equal to 2 times 9.81 times 100 times 10 to the 3 minus 100 squared all over 2 times 450, which when I run that, because sometimes I do have emulators, but I feel like that's not going to be as interesting for you guys because you watching me push buttons is not going to teach you anything. Damn. So 2000 by my numbers, it would be 2170 degrees C. And so if it started at something like minus 265, which is very close to absolute zero in deep space, that would give you a final temperature of basically 1900 degrees C. And if that falls into some, now that is unlikely to be realistic because this neglects the energy lost to the air, as we said before. Oh, someone suggested a question. Let's go and do yours. So a copper block of mass, so that's copper, it's 2.5 kilograms, is heated to 500 degrees C and is then placed on a large ice block. Find the mass of the ice it melts. So the C for the copper would be 0. I assume you mean 390 joules. So let's say it's 390 joules per kilogram per Kelvin. And let's say the specific, the latent, not ml, let's say that the latent heat of fusion for the ice is 335 kilojoules per kilogram per Kelvin. All right, so again, whenever you're doing any sort of question like this, you want to first start with the word equation. So the energy lost by the copper equals energy gained by ice. And I think we are going to have to make some assumptions here. So we are going to have to assume that the copper, all the energy goes into melting the ice, but not heating the water it then forms. Is that realistic? No, but it is a simplifying assumption that I am going to make. The energy lost by the... Now, in order to reach thermal equilibrium, it's not going to melt all of the ice. So the ice will stay at 0 degrees C. So in order for this to reach thermal equilibrium, this copper will have to reach 0 degrees C as well. So the mc delta T here will equal the ml here. So this would be the mass of the copper, and this would be the mass of the ice. Now, the mass of the copper is 2.5, specific heat capacity, 390. The delta T would be 500, because it's going from 500 degrees C down to 0, where it stops melting the ice. And this would equal the mass of the ice that melts that we're trying to calculate times 335 times 10 to the 3. And so this actually ends up being a fairly simple equation and rearrangement here, where we do 2.5 times 390 times 500 all over 335 times 10 to the 3. And we find that the mass of ice that gets melted is 1.46 kilograms. So these questions I always find very easy, but only if I start with a word equation that guides my thought process. Once I see that written down on paper, I know exactly what I need to do to get to the end accurately. And I never lose track of like where I am, because I'm like, okay, this is what it all means. So starting with a word equation is my top tip today for any thermal question. Excellent question. So someone says before, okay, I understand. So we spoke before about this, a ball falling. And so this is the GP, right? Someone raises a good point. Hang on, what we said before, what was the definition of internal energy? Internal energy was the sum of all the kinetic energies and potential energies of the particles, which is why this is confusing, because now we have a potential energy and a kinetic energy, and it's not the sum that makes up the internal energy. But remember, the internal energy is the sum of the kinetic energies and potential energies of the particles. Whereas this, so that's on a molecular level, whereas this is about the GP of the macro object. So there is a difference between raising the potential energies of the particles by separating them, by melting it, which would happen when the ball stays in place and is melted. That's different than just raising them up in physical space, and so raising their GP. So that's really interesting. Heat required. I've got 3 minutes left, so I don't know if I'll finish this, but I can give it a go. So the heat required to convert 1 kilogram of ice at 0 degrees C into steam at 100 degrees C. In order to do that, I would need to know the latent heat of vaporization of water, which I'm not sure I know. If someone can look that up and drop that in the chat real quick, I'll see if I can get through the rest of this. In this case, let's talk about a word problem. So this is now what would need to happen? I would need to have m times the specific latent heat of fusion. Thank you very much. Wait, what does cal per gm mean? And then I would need to do an mc delta T to raise it up to 100 degrees C. And then I would need to do m times the latent heat of vaporization in order to convert this water into steam. Thank you very much. So this obviously depends on the mass. So let's do it for, is it 1 kilogram? Yeah, let's call this 1 kilogram of ice. What you would need is the specific latent heat of fusion, which would be 3.36 times 10 to the 5, plus the 4,200 times the 100 degrees. You need to go from 0 up to 100. And you would also then need to put in the 2.26 times 10 to the 6 joules to then convert that 1 kilogram into steam. And so putting this all together, 3.36 times 10 to the 5 plus 4,200 times 100 plus 2.26 times 10 to the 6 would give you a cool 3.016 times 10 to the 6 joules would be required to boil 1 kilogram of ice, basically. All right, I think that is a very good place to stop. These questions, I have no idea. These questions have been presented to me in the chat, and so these are kind of blind. I would rely on any resources you have for further questions, be that the textbook or past papers or online resources like Physics Math Tutor, Save My Exams, something like that. So you are very welcome. And again, that top tip for any thermal question, never start anything until you write a word equation so you know what you're doing. That is the main thing, I think. That's the sort of guiding principle that always helps me out in thermal, because you can lose track of your energies really quickly. And that also applies to energy when you're talking about energy, power, work done. So you saw that we were talking about like GPE going into kinetic plus internal. Any sort of word like energies, I need to know the story first. Brilliant. So I hope that you found that, guys, useful. I now have to run for a session, but I will see you guys on Monday as usual for another math paper live solve, and then hopefully next Wednesday as well for another physics, where we might be going through the gas laws. Would be a really top recommendation, actually. That's probably top of the list, but also some waves as well. But right, thank you guys for joining. Take care, and thanks for being so active in chat. I really like it when you guys bring the questions like that, so keep it coming. All right, I'll see you guys next week. Take care. Bye-bye.